Уважаеми млади приятели на математиката, добре дошли на последната лекция от серията от лекции на френски математици. Днес няма нужда да представям нашия докладчик. Това е професор Пампу, който вече го познавате. Искам само да ви напомня, преди да дам думата на професор Пампу, че утре в 3 часа във Френския институт, който се намира на площад Славейков, няма как да го сгрешите къде се намира, има и френския флаг. Ще имаме дискусия за събитието, а специално за вас това ще е още една възможност да поговорите с нашите лектори. Имаме там достатъчно време. Сега искам да изкажа специални благодарности на няколко конкретни хора за провеждането на това събитие. Освен организациите, които вече споменахме в началото, по време на откриването на събитието, искам да благодаря специално на няколко човека, без чиято помощ и подкрепа това събитие нямаше да се състои. Това е директора на Института по математика и информатика, член-кореспондент професор Петър Бойваленков. Това е академик Олег Мушкаров. Това е член-кореспондент Николай Николов, председател на Съюза на математиците в България. Това са и служителите на Института по математика и информатика към Българска академия на науките. Лилия Симеонова, Константин Делчев и Ана Брънзова. Специални благодарности на всички тях, които помогнаха за една добра, гладка организация. А сега давам думата на професор Патрик Попеску-Пампу.
So, thank you very much. I told already at the beginning of my first talk that I was very honored. I continue being honored to be here and happy that you are back. So I hope to interest you with a theme which again does not come from my field of research. In fact, I was invited a few years ago to give a 20-minute talk at the Academy of Sciences in Paris. A special day was organized by what is called the Perpetual Secretary of the Academy of Sciences, Etienne Gis, about cartography. And he invited people from various specialities to speak about cartography and the art and science of map making. So I'm not a map maker, but he thought about me as somebody who could speak about cartography from the mathematical viewpoint. And in fact, he suggested me to speak about the Mercator projection. I told him that I knew nothing about it, and he answered, well, learn. And I learned. I spent some 3 months reading 5 books and some 30 papers about it, and I found the theme really fascinating. And then I began preparing a beamer, and my first beamer, in fact, I began speaking to present the different views in the beamer, and I saw it was for more than 1 hour. So I had the task to concentrate this and to arrive at 20 minutes. But I did not remove things. Simply in my file, I put percentages in front of them, which meant that I could use that again, thinking that all that work could serve at another occasion. And you see here the occasion came, just I removed my percentages and I embedded myself again in that context. So now don't be afraid, I won't speak only 20 minutes, or perhaps you would have been relieved to be able to escape after 20 minutes. You will have to listen to me a little more. So, the title is Gerardus Mercator and the Art of Spiraling Straight Ahead. The second line is a kind of paradox. How is it possible to have a spiral which goes straight ahead? And in fact, this is precisely what is achieved in the maps done under Mercator projection. So the subject of my talk today will be the Mercator projection. But before speaking about it, let us agree about something basic, that we are speaking about maps of regions of the Earth. And the Earth is idealized as a geometrical sphere. And on the sphere, we have the poles, which are represented by two antipodal points. And we have a grid of special curves which allow us to say where we are precisely on the Earth. Some of these curves are the great circles which pass through the poles. They are called the meridians. And we have also one great circle which is orthogonal to all of them, which is the equator. And then smaller circles which are cut by planes parallel to the plane of the equator, which get smaller and smaller when we approach the poles, here or there. They are represented as red circles here. In order to be able to say precisely where we are on the Earth, we need coordinates, and the coordinates are fixed using this grid. First of all, one needs a reference meridian. Geographically, there is no preferred such meridian. Its choice is fixed politically. Nowadays, it's the one which passes through the Observatory of London in Greenwich. Historically, other meridians were taken as reference ones. So this is, say, the reference meridian. And then one needs a reference parallel circle, and that is fixed geographically. It is the equator. So let's say that the origin of coordinates is here, and then along the equator we measure the angle from the center. Let us call it lambda. Lambda is the longitude. And now from it on the meridian we measure a second angle here on the meridian, which we will call phi, which is a latitude. And happily, longitude and latitude both begin with L, so I had to choose a second letter which is not the initial of the word. So just remember that phi denotes the latitude. It is important because inside my file you will see a lot of times phi. The letter phi systematically will denote this geographical coordinate. So as I told you that the subject of my talk will be the Mercator projection, let us see first a map done in Mercator projection. It is a recent one obtained by gluing views from satellite. It's a 2006 map which you can find on Wikimedia Commons. In fact, all my illustrations come from it. If you get my file, here you can click on all these blue addresses and get immediately to that image. So if we analyze a little, you see that here we have parallel lines. These parallel lines represent the parallel circles on the Earth, and vertical lines here which represent the meridians. The meridians met at poles on the Earth, but here not, as they are parallel, they do not meet. And what happens is that in fact these parallel horizontal lines are taken every 10 degrees of latitude, which means that on the Earth, if you look at these arcs on a meridian, they are equal. But if you follow them here in this map, you see that they get longer and longer when we go towards the poles. And in fact, they tend to infinity, which means that to get the complete representation of the Earth, here we should have an infinite band which goes to infinity both to the south and to the north. This is a main objection which in modern times was taken against this projection. For instance, even in the 1980s, there were big critics saying that this is a map which was used for imperialism of countries from the north against the south, in order to show that in fact Africa counts for nothing. and what is important lies in the north. This is in fact a reason which overlooks something very important, is that this map is done with a precise mathematical purpose. And its construction has to do only with geographical properties of the Earth, not at all with any political ones. Moreover, the critique that things are dilated towards the north produces something like this. You see, apparently here, if you look at the Groenland, it looks bigger than South America, when in reality the surface of Groenland is more or less 1/8 of South America. So each time one has a map, something is deformed. You cannot look on a map and expect to see undeformed all the properties of regions on the round globe. And this is the message which has to be taught at schools, that every map deforms something, and so what is important on a given map is to know what it preserves. And depending on what we want to see immediately, what we want to see rapidly, we use one map or another one. And if one knows this, then one knows how to choose among the maps. Like in a supermarket, depending on what meal you want to prepare, you buy such and such vegetable or meat or fish or something else. Among the maps, it's the same thing. So let us go now nearer and analyze what was the question which was asked, which led to this map. First of all, a Mercator map was not used only for region of the Earth. Here you see a map from 1911 of regions of the planet Mars. So again you see these vertical segments here which get longer and longer. They correspond to arcs of meridians on the planet Mars, which are equal on the globe of Mars. So this is a sign that you are on the Mercator projection, but this does not determine it. This is important. If you look at this phenomenon, you still don't know that the map was done under the Mercator projection. We need a very precise condition to lead at it. Here is a second way of making maps in which arcs which get nearer the poles are represented by longer and longer segments on your map. Here you see the spirit of what is called a cylindrical projection. We have the globe, which again is thought as a perfect sphere. Here we have the equatorial circle. I represented here the North Pole. And now you look at the vertical cylinder, which is tangent to the sphere along the equator. And we will project the sphere on the cylinder from the center of the sphere, which I called O. So you see this point P goes to P prime. So here you see that only the line ON is parallel to a generator of the cylinder and will give you nothing on the cylinder. All the other points here are represented by something, but when P converges to the North Pole, you see that P prime goes to infinity here. So again, you have this phenomenon that to represent the whole Earth, you need the infinite cylinder, infinite both to the north and to the south. This allows to take any region of the Earth, push it on the cylinder, and now the cylinder, if you imagine that it is made of paper, just cut it along a vertical generator like this, and then unfold it, and it becomes plain, and you get a map. So this is a spirit of cylindrical projections. And you see that such projections are in fact determined by the way you project this arc of meridian on the corresponding tangent. Here the projection is done from the point O, but it is represented by these segments. In fact, here any strictly increasing and continuous map from this arc to this half line works and gives you another projection. So what is important is simply to make this arc straight and the point N to push it to infinity. These are the cylindrical projections. Or you can have also cylindrical projections which are not pushing n to infinity. A famous one is due to Archimedes and simply projects all the points horizontally. So in fact, n will be projected here, and this arc will be projected till here. So then you get a finite map, you don't have to go to infinity. That map is famous because of the following property: it does not deform the areas. So it means that a region on the Earth, when you project it parallelly like this on the cylinder, and then you look at it on the flat map, will have the same area. So it means that there, in such a map done under the Archimedean projection, will show that Groenland is 1/8 of South America. So now, as you see that this is not a Mercator projection, let us go and see what is Mercator projection. But I consider that we are still not in the correct philosophical mood to answer that. So, a little like Cédric Villani's talk, I will return in history to Ptolemy. But now we will read an extract of Ptolemy's geography from Book 1, Chapter 1, called On the Difference Between World Cartography and Regional Cartography. In modern mathematics, this is called the difference between global and local. So you see already in the 2nd century after Christ, this difference was important in geography for Ptolemy. Let us read. For these reasons, meaning regional cartography, what is put enclosed by straight brackets are in fact parts of texts which were added by the translator to make the text understandable. You have to see that it was translated from Greek or from Arab. I forgot exactly from which sources it was translated. And it was written in another context, so phrases, sentences were built in other ways. So when you translate, you have to add elements which make them understandable in our own context. So very often, to make the reading easy for non-specialists, one has to incorporate such pieces of meaning. So let's start again. For these reasons, regional cartography has no need of mathematical method. I insist on this to see that he is speaking about mathematics. But, so he says, if you are interested in regional cartography, which means representations of small parts of the Earth, then you don't have to deal with mathematics. Mathematics appears if you want to represent large portions of the Earth. So he says, locally we do not need mathematics. In modern times we saw that in fact even locally we need mathematics and a lot of mathematics, but at least for a local geography in Ptolemy's times, he considered that the person who does geography does not need to deal with math. But here in world cartography, this element, the mathematical method, takes absolute precedence or importance. Thus, the first thing that one has to investigate is the Earth's shape, size, and position with respect to its surroundings. So please think about this. You have something, think about Bulgaria, and think about the differences of the shape of Bulgaria, the size of Bulgaria, and its position with respect to its surroundings. And think that these are three characters of any shape in geography, and more generally, of any shape inside a space. And these are, in fact, common problems of geography and mathematics. So that it will be possible to speak of its known part, how large it is, and what it is like, and moreover, under which parallels of the celestial sphere each of the localities in this known part lies. From this last, one can also determine the lengths of nights and days, which stars reach the zenith, or are always born above or below the horizon. So you see, geography does not deal simply with the Earth, but how the Earth is embedded in the cosmos, in the visible cosmos from the Earth. I insist here, you see, the perfect sphere for Ptolemy is not the shape of the Earth. It is the shape of the celestial sphere, and the celestial sphere is to be thought covered by this grid of parallels and meridians. And you project it, say, from the center of the Earth. So at no moment he says that the Earth is spherical. He speaks about the shape of the Earth, and you know, when you see here in Sofia, you see mountains everywhere, it's clear that you are not on a spherical part of the Earth. But what is spherical is the celestial sphere you look at in the night. And this is the way you imagine if you have only your eyes. In ancient times, you could not imagine all the complexities shown by modern ways of exploring the cosmos. So you see here we have in fact a game of two shapes. The Earth, which is imperfect, is not spherical, it has some shape, and the Earth has to be made in correspondence with the global sphere of the night. And this is important because of the following thing. This idea, which you see is present here in the 2nd century after Christ, came back in a different, completely different problem, the problem of definition of curvature in works of Gauss in the years 1820. So say 1600 years after. And Gauss said, now I will apply, in order to study the shapes of surfaces, a basic idea used all the time by astronomers, which is to say, if you are at a place of the Earth, like me now, just stay straight and look above you, which is a star you have above. And in this way, you associate to a place on the Earth a point on the celestial sphere. And you get a map from the Earth to the celestial sphere, and this is called now the Gauss map. But if you believe that Gauss introduced it, yes, Gauss introduced it in the problem of curvature, but it is already here in Ptolemy. So you see, in fact, it's very difficult to say this precise idea was born at such a context. I think precise ideas are like birds. They are always flying from region to region, from time to time, and an invention is to see that that bird can bring something in your garden. But a bird does not belong to a garden. The birds have their own lives, which are mysterious, and we are lucky enough if at some moment we see that the bird brings some grain which gives you a nice tree. And this, I think, is one interpretation of what said Cédric Villani, that it's very important to speak with other persons, because you will get birds through what you exchange with other persons. So let us proceed. Now that we read something from Ptolemy, let us see some maps done following the algorithms described by Ptolemy for building maps. Ptolemy described several ways of projecting parts of the Earth, and what is called the first projection of Ptolemy is a way to draw the meridians as straight-line segments, but straight-line segments which are radial. They converge to a same point. And the parallels are represented, in fact, as the circles which are centered at that point. So here you decide to represent the grid of parallels and meridians in this precise way. And then you have the problem of representing the known parts of the Earth in this grid. This is a second problem. What we will analyze today is just the grid we use. Once a grid is drawn on your piece of paper, then comes the most sophisticated part of cartography, which is to gather information of all the travelers, the merchants, which say where the cities are located, how many days of travel you have to use to the north, northeast, till you reach a mountain. And all these taken together give you instructions for placing the parts of the Earth. And I won't speak at all about this second part, which I think can be fantastic for a cartographer, because he needs to read a lot of documents and then he learns a lot about the structure of the Earth. our problem will be simply which grid to draw first, before putting then the images on it. Let us see what is called the second projection of Ptolemy. In the second projection, both parallels and meridians are represented as arcs of circles. So you see here that there is a transition between this arc which is curved to the right and this one curved to the left, and there is one which is represented straight, which is here an axis of symmetry. And there is a rule which I forgot for choosing the centers of these arcs. But you have it, you can go and find on internet the book of Ptolemy and see his rules of drawing this second projection. Simply you see here that he said that one can use different rules for choosing the grids of parallels and meridians. These, of course, are representations which come from much more recent times. You see this is from 1487. Of course, absolutely no map arrived till us from the time of Ptolemy. But what arrived was a text describing how to draw these grids. Now, we saw two ways of making projections coming from Ptolemy's time. I showed you a central projection from the center of the Earth on a cylinder. I spoke about general cylindrical projections. I mentioned the Archimedean projection. So finally we discussed four. I promised that we will concentrate on a fifth one, the Mercator projection. But in fact, through the ages, thousands of projections were used for making maps. And if you find this theme interesting, I think you will love this book, Flattening the Earth by John P. Snyder, 2,000 years of map projections, which tells the adventure of all this art of doing projections in geography. Now, let us getting nearer Mercator. I show you here a cartographer at work. This is an image done in 1318, the cartographer Pietro Visconti, and this is part of a manuscript, which is now in Venice. You see him here doing a map. And here you have a fragment of the same map, which is here. And on this fragment here, you see some lines. So again, you have a kind of grid, but you see that in these grids, lines originate from some points here. You see two such points. So let us see now from farther the kind of map he was doing in 1318. This is called a portolan. So this is one of his portolans of the cartographer you just saw illustrated. What is a portolan? Is a map which was used for people who navigated from port to port, from harbor to harbor. So if you see, we have here part of Western Europe. Here, modern France, Iberian Peninsula, with modern Portugal here and Spain here. Here, Great Britain and Ireland. And you see that you have a lot of crowded information along the coasts. Those are precisely the ports. So this was information which was essential for people which were going in ship from port to port. You have all the names which are represented, say, perpendicularly to the coast at each moment. And you see that some more important ports are represented in red, the others in black. So you have a lot of conventions of representation, and this allows us to see that a map has a purpose. It has, in fact, persons who are interested in that precise map. And this is the same as what is essential to do when you prepare a talk. A talk is like a map. You have to know to whom it is addressed. And you construct it thinking about those persons. So for me it was absolutely compulsory to give a talk which is understandable by you in high school. But not any person in high school, by persons already interested by mathematics in high school. If you were arbitrary people from high school interested, for instance, in literature or something else, I would not have put the more precise mathematical parts in it, into which we will arrive. You will see that we will have parts when one needs to be able to understand formula. So that I put because I was thinking about you and your taste, which is already developed for mathematics. So you see, it's like on a map, you have to know to whom the map is addressed or to whom a talk is addressed in order to construct them. Inside the continents, you see that you do not have towns. For people using this map, this was absolutely not important. But what was important is to know to which country or duchy they belonged. And those are represented by flags. So in this way, using the flags, they knew at each moment that city under which rules they were governed. Now let us see again a Portolan 200 years later by Visconte Maggiolo from the 16th century, but now at a greater scale. You see, the previous one represented only this part here of Europe, and now the whole actual Europe and Northern Africa. And here you see that you have more details about the interior of the continents. Also some geographical details like mountains. Here, the Balkans of actual Bulgaria. And you have also some lakes and other mountains and some details of internal cities. But the main information is again this crowding of cities along the coasts. So that's why it's still a Portolan. And please pay attention about now the grid. You see that you have a whole grid of lines, but it is much more complicated than simply the grid of parallels and verticals, the meridians. You see that this grid, in fact, is structured by some points here, which turn around a circle. And if we go back, you see again the same structure here. This, in fact, if you look carefully, you see that they are equidistant, and in fact there are 16 of them. These 16 come from a refined way of looking at directions. When you are navigating at each moment, you have to decide if you are going to the north, the south, east, west, or say to northeast, northwest, etc. If you say northeast, it means that you are taking a straight angle here to north and east, and you are taking the bisector. And say northwest, you take a second bisector. In this way, if you are looking at the rays emanating from this, you get 8 rays. The 4 initial rays, north, south, and east, west, and the 2 bisectors, which give 4 more rays. But this is not enough. To have more precision, they bisected once more. And that's how you got 16 rays getting from each such point. These centers, with rays emanating from them, were seen as compass roses. So in fact, we have here a big circle of 16 compass roses. And again, you see it here. And you see that those centers also sometimes were decorated. You have here a lot of decorations, but not for all of them. Those arriving in the middle of the sea are not decorated. I don't know why was present this difference. So you see that you can have a lot of interesting cultural questions which pop up if you look carefully at the map. Let me continue now and see the same kind of Portolan, which is a world map, representing the known world in 1543. What was known and what was believed to be the reality. So look here at South America. So you see that in 1543, the shape of South America was not at all clear. And look here at North America. Here, they did not know how to continue the coast. This part of North America was terra incognita at that moment. And if you see how Europe is filled with things, you can compare here with Siberia or North America to see how that was a field for research. And in fact, those of you who will do research, you will probably want to know in which directions we have terra incognita, such that you are not inside a crowd and you will have a place for your imagination and your exploration. Some researchers like to be in a very crowded field with a lot of competitions. Others prefer not to have too many persons there and to have a sensation of vastness, like exploring, say, North America in the 16th century. And here, you see, the grid is the same, with all these lines which emanate from these roses. Those lines were very useful for navigation at the small scale, at the local scale, here, say, in the Mediterranean. Because people who navigated, if they wanted to go, say, at 45 degrees with respect to the east, they just took the bisector here, and they say, if I follow this, I will arrive at this point of Italy. And they believed in their map. But for such maps at this big scale of the world, when people began to cross from Europe to Americas, big errors of navigation occurred if they believed that this indicated the southwest direction, for instance. So appeared problems of navigation. And this is a source of Mercator projection. Let us see. You see, we are in the years 1543. So the problem pops up at that historical moment. Pedro Nunes, who was a Portuguese cartographer, wrote several treatises, and he made appearing the difference between the fact that if at some point you fix a direction, you could go following that direction along a great circle, but that great circle does not give you the correct line on which to navigate on the same, under the same angle. So he said that there is a second kind of lines on the surface of the Earth, which he called rhumb lines. Rhumb was a Portuguese word which is near as a structure to the actual Spanish word rumbo, which means direction. So he said he called them rhumb lines as lines of constant direction, which means that along such a line you are following on the compass and you always see the same angle. And he said that to have maps in which such lines are drawn would be essential for navigation. Because in this way, the navigator would know that by following a constant angle, he would know where he would arrive. Those lines are not these ones. So Nunes said, we should, at the scale of the world, represent another grid of curves on the Earth on which we draw the rhumb lines. You will see here I'm starting quoting papers by two Portuguese authors, Leitão and Gaspar. Here it's a paper called Globes, Rhumb Tables, and the Prehistory of the Mercator Projection. I read, I think, some 10 papers of these authors, and I found them fascinating about this. If you are interested in the way this way of thinking differently about the cartography of the world for navigation purposes developed at the period, their papers are really extremely interesting. And here in my beamer I cite several of them. So let me come back to this treatise of Nunes from 1537. He said that such lines are important, and he also sketched some of them. So you see, he sketched a lot of them in a way which makes the figure a little difficult to understand. I think that perhaps you can see that each such arc is part of a rhumb line, but how it follows, here we have to continue to which one. That's why I put here some colors, so that you see two of the rhumb lines of Nunes in 1537. So this is in fact a sketch of how they appear seen from a pole. And the difficult problem he had is to know what happens with such a rhumb line when you get near the pole. Here on the blue one, he stops, he does not continue. But the red one, you see, makes a turn and then he makes it arrive to the pole. And indeed, in 1537, he believed that you did not even turn completely once and you converge to the pole on such a rhumb line. But this was false. In fact, here you see the birth of a problem. You have an idea of a kind of curve on the surface of the Earth, which has a property to cut every parallel under, or every meridian under the same angle. These are the curves. And here you see the subject of research. What are their curves? What are their shapes? And in particular, what does it mean? What are their shapes? A sub-problem, what happens to those curves when they approach a pole? And you see here how you have a sub-problem which is similar to the problems you receive for Olympiads. And I hope to show you how the problem emerged from a larger problem of research. And in fact, I had a transition from my time when I prepared Olympiads like you and the time when I decided to be a researcher, because at some moment I had the revelation that Olympiads did not teach me how problems were born. And I say I want to discover, in fact, what is the source of problems. And that's why I began at the same time interested in mathematics and in the history of mathematics. It's something which does not occur often. I see in my colleagues, the majority of mathematicians I meet are not at all interested in history of maths. They are very happy with learning theories logically, knowing this theorem implies this theorem. But in fact, I am not at all happy with pure logic. What I want to see is how the questions which at some moment led to answers called theorems or propositions were born. And this is precisely the guiding spirit of my talk today. I try to show you on this precise problem the birth of things. And you see that you cannot arrive and touch births if you don't go and look at the documents. And you never know precisely if things happened like this. But you can touch some documents which show you incipient ideas. And what I show is a result of my inquest on this theme here. So here appears a problem. How do rhumb lines converge to the poles? And you see that the first conjecture of Nunes was false. A rhumb line, in fact, does not converge to the pole in this way. Let us come back. We saw this was 1537. 4 years later, we have already a globe on which rhumb lines are drawn. And they are drawn on a globe by the hero of my talk, Mercator. Mercator was a cartographer, very famous in his time, who did both flat maps and globes, and not only terrestrial globes, but also celestial globes. And there is a museum. I live in Lille in the north of France, so in, I don't remember how much time, less than 1 hour by car, I can reach this museum, Mercator Museum. And I was preparing my talk, so I had passion for this, and I spent 2 hours in the museum, and this was horrible for my children, who were not preparing a talk, who were, I think, around 10 and 14 at that moment. So then they told me that they will never return with me in such a museum. So that's life. And you see here that you have these lines and you can follow them, but unhappily Mercator stops drawing them when he gets near the pole. He does not continue. So in fact, this problem, what happens near the pole, is avoided here. But it's avoided in the way we saw on the map of the Earth. Some parts have nothing inside, showing that this is terra incognita. So you see, the fact that a line here stops in somewhere is a sign that there is a problem to inquire. So be sensible to this. When you hear, say, a talk and you see that at some moment the talk stops, ask the end after, and then perhaps you will discover that after it is unknown. And for researchers, this is absolutely important. It's more important to know what is unknown than what is known. Because as a researcher, you want to go in the unexplored. So somebody, a mathematician I appreciate a lot and I admire a lot, whose name is Norbert Acampo, told me that when he became a researcher at the beginning of the 70s, it was much better for young people than now. He said, in that time, when you went to a seminar, people were telling what they do not know. Say, now you go to seminars and everybody shows its muscles. Well, I know this and this, and you learn nothing about the unknown. So you have to go then and discuss with people. Well, okay, you showed me that you know all of this, but what don't you know? And for researchers, it's very important to know what's unknown. So it's very important, when you have a universe to explore, to see where the lines stop, because then we don't know what happens with them. So let's look at what happens with them. First of all, let's see a little how such a globe was made. Well, it was made using flat pieces of paper, which was in fact cut in such zones, and the zones which are sufficiently, comment on dit, fine? Sufficiently thin, thank you very much, Bernard, so that you can glue them on the globe and give the impression that the globe is completely covered. So you have to imagine that independently built zones are glued carefully here till you don't see that you have several zones. So you see that it was a problem of computation, because these lines which seem to go continuously from one to a zone to the next one without breaking, in fact, had to be done. It arrives here and then it continues in the next one. And you have to give the impression of this continuity of direction on the globe. So you see already, as said Ptolemy, that at this global scale you have real mathematical problems which pop up. So you discover here why a cartographer dealing about the representation of the Earth had to know and to study mathematics and to be able to solve mathematical problems. So here you see also that this is not a globe for people only sailing, because you have a lot of information inside the continents, not only inside the seas. But inside the seas you have this grid of curves, rhumb lines going in all directions. Now let us analyze just such a part of a zone, like a time zone, and only the part lying above the equator. It is made of two meridians meeting at the North Pole and a small arc here of the equator. This builds what is called a spherical triangle, and you see that in this triangle, here on the base, we have two right angles. This shows you that the sum of angles of this triangle is bigger than 180 degrees. And in fact, this is a theorem. Any spherical triangle has sum of angles bigger than 180 degrees. And this was proved at least in the 2nd century after the Christ by Menelaus, who wrote a book called Spherica, who tried to do for the sphere what Euclid did for the plane. And in particular, he proved this fact with reasoning similar to the reasoning of Euclid. So if yesterday I told you about this way of thinking to make common proofs for plane and spherical geometry, I was already preparing you a little to this spirit of cartography of the globe. There is a very interesting recent article published in American Mathematical Monthly by Athanas Papadopoulos called The Three Theorems of Menelaus. in which he explains you the proofs of those times. Nowadays, the proofs would be explained in a completely different way. So if you want to enter in the way one could do the geometry of the sphere in the 2nd century after the Christ, this is a perfect entrance, this paper of Papadopoulos. He wrote this because, in fact, he edited a translation to English of the spherical of Ptolemy, which did not exist before. So now if you are interested in that, you can even look at this translation. So to see that all the objects we are looking at are in fact objects done in the 16th century which were considered to be very precious, very expensive, and the way to show the wealth, we can look at a very famous painting called The Ambassador by Hans Holbein. And I won't discuss about the problems of history of art related to this. You can find a lot of things on internet about the ambassadors. Do you know why this painting is famous, mainly? Yes? Exactly. Where? Does everybody see the skull? So it is here. But you see, it's not clear that it is a skull. In fact, this painting was done in order to be put in a precise place, such that people entering the room, they entered, and if at that moment they turned their head, they saw things such that nothing was clear in the painting except the skull. You saw first the skull. And in fact, here you cannot see clearly both the scene, you have the sensation to see clearly, and the skull. You need these two perspectives to see either one or the other. And in fact, this is part of a much more general family of paintings which were done in order to recall that we are mortals and we have not to be obsessed by richness, which are represented by all the objects you see here. We have to think also of what happens after this terrestrial life. But perhaps there are other meanings of the painting, and you can begin to dream. Was it done for other purposes? Why ambassadors? A sign of the fact that they are ambassadors is that you have here two globes. One is a terrestrial sphere here, down, and one is a celestial sphere. And in fact, if you go and look carefully at this terrestrial sphere, this was done by current researchers, you have ramp lines represented on them. So in fact, now that you saw the we are in 1533. We do not have ramp lines. Sorry. But we are just before the moment when ramp lines begin to be represented on the globe. You see here also, instruments of astronomy which were essential then for navigation. Say you have globes, you carry them with them, but then you have to know where on the globe you are at some moment, and you need instruments. So in some sense, here you have a lot of the objects which were essential for the exploration of the new world which appeared for Europe at that moment, which are the Americas. So finally, let us come to what is called Mercator's world map. It was done in 1569. And for me, it was a mystery. I believed it was a central object to be shown in the Mercator Museum. And I visited carefully all the places, all the rooms in the museum, and I did not find it. Till at the end, in a lobby without light, it was on a wall there, without explanations, with nothing. I don't understand why this map was not shown as a prominent realization of Mercator. For me, it's a kind of curiosity why in 2020, just before the COVID, this was not considered to be an important piece of the museum. Perhaps because of the critics which appeared in the years 1980 that it's a map which shows the colonialism of the north towards the south. I don't know, perhaps for such a bad political reason. But this is completely crazy because, as you begin to see, this map was done for solving a mathematical problem. It had nothing to do with colonialism or something else. So what do we see here? Well, I think you see clearly that you have still these roses. But now, from these roses, you see lines which originate, again, equidistantly here. But now, for the first time, they represent the rhomb lines. So the problem solved by Mercator is to make a map in which the lines drawn on the flat piece of paper represent the rhomb lines, and moreover with the correct angles. The fact that the angles measured here on the flat piece of paper are the same as on the Earth is called conformality. Conformal, it's a Latin name saying that we have the same shape. So here, the fact that they have the same shape does not mean that globally the shape is the same. Is to say that what is most important in the shape is a local situation, and the local, think of a shape, imagine of a triangle. A triangle is a global shape, but you see that its most important points are the three vertices. So importantly that you can keep the vertices and forget the edges. And you can reconstruct the triangle by taking the convex hull, like in Tessier's talk. And then when you do this, what appear are angles. And then a triangle, if you deform it by making a map, it can appear with curved edges. To say that that map is conformal means, well, I get a deformed triangle, but the angles I see at the vertices are the same. So conformality means that the shapes are preserved very near every point. So in particular, the angles we measure here are correct. You see that those roses are preserved, but something disappeared from the portolans, which is what? What's the difference between the representation of roses here and the representation of roses in the portolans? They are not any more regularly distributed on a circle. They are in fact chosen all the time inside the oceans. And I wrote to Gaspar, one of the specialists I told you about, if he understands the way they are chosen, and he said no. But perhaps there is a rule. Where did Mercator choose to place these points? So this is also a question for you. If you click on this, you have access to this map, and in fact you have also some smaller parts of it, for instance this one. And you can go and look at the details. So for instance, you see how crowded was Europe and how crowded was Africa is a sign of the conscience of the earth of European people at that moment of history. And compare here with North America. So you see here that this is called, in fact, India, and this is a Gulf of Mexico. So you see this becomes now a modern political problem, how to call this Gulf. Already in 1569 it's Gulf of Mexico. And if you want to change its name, you can call it Gulf of India, because here this was India. So again, you see here that we have terra incognita here, and this is much better known, this part of actual Mexico, than this part of Canada. This is a portrait of Gerardus Mercator Rupel Mundanus. This is an allusion of the place where he was born. He was born in 1512, so here it's a representation done when he was 62. And you see the representation with him using this kind of compass without a pencil here. This is a compass which is made just to report angles from part to part on the Earth. And he represents here one of the globes he was maker of. All these maps, the specialist Gaspar explained me, were manipulated with such compasses, because in fact they were very expensive and you could not draw any line on them, and pencils did not exist. So you used them only to report lengths on the map. So this was in fact the main tool which was used either on globes or on the flat maps. Mercator was interested, in fact, in all aspects of cartography, everything, so not only the mathematics of those grids, but also in the way to represent correctly all the shapes and information. This is, in fact, all the work of a cartographer, but also in the way to draw in a legible way on the maps. So, and this is demonstrated by the fact that he published a book of cartography. This is a picture I took in that museum, where he shows, in fact, how even to take correctly your pencil in your hand. This is not correct, and this is correct. Unhappily, I could not find in that museum a modern edition of this, otherwise I would have bought it immediately. I found these pictures absolutely wonderful. For you, I imagine it's absolutely clear that if you want to see in a book maps, the book is called an atlas. But this was a decision of Mercator. The first atlas was Mercator's atlas from 1595. He worked during a very long time to the maps of that atlas, and this was published 1 year after his death. And here you see the word atlas, but he chose it in reference to Atlas, which is here. So let us see who was Atlas. I put here an extract from the first thing where you can go now in modern times to get information from Wikipedia. In Greek mythology, Atlas is a titan condemned to hold up the heavens or sky for eternity after the titanomachy. If you want to know what is titanomachy, I leave you at home, you can click on that. Let's continue reading. Atlas also plays a role in the myths of two of the greatest Greek heroes, Heracles and Perseus. According to the ancient Greek poet Hesiod, Atlas stood at the ends of the earth in extreme west. Later, he became commonly identified with the Atlas Mountains in northern Africa and was said to be the first king of Mauritania. Atlas was said to have been skilled in philosophy, mathematics, and astronomy. In antiquity, he was credited with inventing the first celestial sphere. In some texts, he is even credited with the invention of astronomy itself. The term atlas, I skip something, has been used to describe a collection of maps since the 16th century when Flemish geographer Gerardus Mercator published his work in honor of the mythological Titan. The Atlantic Ocean is derived from Sea of Atlas. The name of Atlantis, the mythical island mentioned in Plato's Timaeus dialogue, derives from Atlantis Nessos, ancient Greek, literally meaning Atlas Island. So you see that this name, in fact, has a lot of ramifications. And it's also extremely important in modern mathematics, because in modern mathematics, a space in general is defined usually using an atlas. More precisely, if you continue doing math after high school, if you study what is called differential geometry, the fundamental objects you will study using differential geometry are generalizations of the sphere, which are covered by charts. And that's why all those charts say how they are precisely to be glued, and they are called an atlas. But you see that this name atlas propagates, and it arrived to mathematics from a decision of Mercator for putting all the charts together under the figure of the mythological Titan Atlas. So let us come back to Nunes, who asked the question which led to this Mercator projection. This is another book from 1566. Because it was very difficult or even impossible for seafarers to trace on the globe lines similar to those, that is, the rhomb lines followed by ships. The mathematicians imagined a plain description of the world, not only adapted to their art of navigation, but also much easier. In this representation, straight lines are traced representing the rhombs of the same name. Because they are parallel, they make equal angles with all meridians or north-south directions. So here, in fact, there is a problem of history of maths. It's not clear about which mathematicians he is speaking. It being from 1566, and here the map of Mercator from 1569, this tends to indicate that Mercator, in order to make his map, used, in fact, results of mathematicians. But which mathematicians? Here there is a terra incognita. What does Nunes speak about in 1566? And what was this work of mathematicians at the base of what Mercator did? In fact, we have nothing which arrived till us who tells us how Mercator made his grid of lines for his projection. As I told you, once the grid is done, then you can put all the information which come to you from other cartographers and from navigators and merchants. But how was the grid done by Mercator? We don't know. We have only conjectures. In fact, the first book, as it is known now, what we believe is the first book, in which a method was explained in order to build Mercator's grid, was published in 1599. And here you see the frontispiece of the second edition from 1610. It is due to a British mathematician called Wright. The title is Certain Errors in Navigation Detected and Corrected by Edward Wright, with many additions, etc., etc. And here below, you see, in fact, a map of the Earth with all these lines, and in fact it is done in Mercator projection. An indication of the fact that it's Mercator projection is that, again, you see here Groenland bigger than South America. So I think this is a sign for you. Is it Mercator projection? Look at Groenland, look at South America. If they seem to have the same area, it's a good indication that you are in front of such a projection. So I want to show you now Wright's method. And there we will enter into mathematics. Into mathematics, which is more sophisticated than just looking at sums of angles. In fact, we will get to one of the precursors of integral calculus. Here, it's in fact a page from that book of Wright, which is a numerical table he used in order to construct the map. So first, we will see how he used that, but you have to know that behind that map you have numbers. So this is not something of modern computer sciences, that everything is number. Here you see the map with some geometrical object was performed by first computing tables of numbers in 1600. So the first question we have to ask is, what happens when we take parallel circles which converge to the North Pole? So we want to understand, if we followed here a latitude called phi, what is the radius of the parallel circle? So this is in fact a very easy trigonometric problem once we look correctly. Here we are in space, but in fact we have to look at such a meridional disk and only half of the disk. So this yellow disk, which is bounded by a meridian, I redraw it here on the right. So here you can imagine that this is part of the trigonometric circle. But now you see that here in spherical geometry you have to be able at each moment to see the trigonometric circle in many different guises, because you have many different disks of section of the sphere. So as always, the plane geometry of Euclid seems to be a game in a single plane. Once to begin to learn space geometry, you have to be able at each moment to do plane geometry in 2, 3, 5 different planes, and the art is to think in the correct one. So here, the one which makes you understand everything is this one. Say, phi is in fact the measure of this angle here. Because we have here a parallel, it means that this plane is parallel to the equatorial plane, meaning that this radius here is parallel to this one. So you have this equality of angles. So you have phi also here. And now in this triangle, the hypotenuse is the radius of the circle. And by convention, we take it to be 1. So this is being 1 and this being phi. This is the cosine of phi. So you see that the rule is that the radius of a parallel circle at latitude phi is the cosine of phi. Let's remember this. And now is a crucial moment when we will understand the method of Wright. I repeat, we have no clue if Mercator thought in the same way. But this is exactly what Wright explains. Now, what we want to do is a problem. We have here a zone on the Earth, and we want to represent it as a vertical band here. And we want to know, say, we have a point here of latitude phi, and we want to know at which height to put it. So the question is, this one, how to represent it on the flat piece of paper. So Wright takes this meridional arc and subdivides it into small arcs of the same length. Let us call them delta phi. The notation is modern. This delta phi, you cannot find it in Wright. So always, when people explain new things from antiquity, first one has to make an anachronism. We have to explain them in the language of nowadays. Still we understand. And at the moment when we understand, we have to say, well, but how did they express that? I won't enter there. I won't show you the precise language he used to express the same thing. That is a crucial problem for a historian of mathematics. A historian cannot stop at the moment of anachronism, but anachronism is crucial for the first understanding, which is the first step of history. So, we divide here in small arcs of the same length called delta phi, and then only the zone is chosen such that here on the equator we have also an arc of delta phi. So the starting datum here was a meridional arc. We fix a latitude, we divide in equal arcs, and then that small arc we put it here on the right. And now comes the fundamental insight. If you do not see the Earth from far away, here, for instance, it seems that the Earth is flat. Here, well, this is flat, it's a plane. Here, there, you feel you are on a plane. So small parts of the Earth seem flat. And this is the idea we have to use at this moment. It means that if we took here subdivisions which are sufficiently small, all these small parts of spheres, we have to think about them as flat. And at that scale, the meridians seem parallel. And because the parallels are orthogonal to the meridians, those are small rectangles. So what we will have to do is here on the flat piece of paper to represent all of them as small rectangles. Here, the rule is we do not deform this length. Here we had a length, longitudinal length delta phi, it will remain delta phi. And the first rectangle here, delta phi, will be a square delta phi. But now when we climb, we do not have any more here a square, because the radii get smaller and smaller. And so it means that if the angle here was delta phi, these parallel angles, here's parallel arcs, get smaller. By what? The factor of proportionality is the cosine, which we just saw. It's the radius of the parallel circle on which we are. So it means that here we have to draw some rectangles with new proportions, which are in fact cosines. And if you look correctly, you see that because these horizontal lengths are always delta phi on the plane, here what you have to put is delta phi divided by the cosines of the heights at which you are, which are latitudinal heights. So you see, this is the rule of doing this. And this is exactly the formula used by Wright for his constructions. So for instance, if I divide it here in 4 pieces, what I would get for the height at which the angle phi 4 gets, which I call mu of phi 4, mu is an initial of Mercator, it's my notation, it's not Wright's notation. Mu of phi 4 is approximately equal to delta phi multiplied by the sum of inverses of cosines. And you see that the idea which leads you to this is this idea that for very small pieces of the sphere you have something which is flat and that you preserve the angles. And that's why here when you had straight angles, they should be represented as straight angles. This is conformality. And it is this conformality which makes that the curves on the Earth, which keep a constant angle, will give you here on the plane curves which keep a constant angle with the horizontal lines. And please pay attention that you can define lines in the plane exactly like this, as curves which cut all the horizontals under the same angle. This is not the definition of Euclid, but this is the viewpoint on lines which is adapted to understand this cartographical problem. So now let us see if we divide that arc in n of phi parts. What Wright says is that we have to take the sum of 1 over the cosines times delta phi. And I chose this notation with delta phi just to make the analogy with the modern formula which comes after a Leibniz text of the end of the 17th century. In modern way, what you have to do is say, instead of taking a finite delta phi, Leibniz tells that you have to take an infinitely small delta phi. And then you have to add an infinite number of such quantities, which he denoted in this way. In both notations here, we have an initial which represents a sound S from sum. This is a finite sum, this is an infinite sum. This is a finite sum of finite quantities, which was the way Wright was thinking about that. This is an infinite sum of infinitely small quantities. But here we get equality. Mercator's function is equal to this integral. So I think you are accustomed to say, well, perhaps I go to an Olympiad or something, I receive this integral, I have to compute it. And yes, this is an integral normally you learn to compute at high school. But if you compute it, it is because you say, cosine, what I do is cosine, I know that I should pass to some rational functions by using tangent of phi over 2 or other tricks like this. Now I want to show you that this was again an adventure, how to compute this integral in the 17th century. I won't show you a computation in modern way, which can be done. I did it, and compared to what I will show you now, I was much less happy. I will show you an absolutely marvelous way of computing this integral geometrically. I don't know how they arrived to think like this, but it's a wonderful geometrical way of computing an integral. So what I want to show you is that this integral is in fact equal to the logarithm of the tangent of pi over 4 plus phi over 2. And we will reach exactly this expression from geometry. We will see precisely popping up with a geometrical interpretation the angle of pi over 4 plus phi over 2. And we will see something which is a tangent of that angle. And then we will see why logarithm appears there. You have to see that Wright published his book in 1599, logarithms did not exist at that moment. They were created by Nepper in a slightly different variant around 1610. Nepper was a Scottish mathematician. By the way, Wright translated Nepper's text published in Latin to English. So Wright got immediately interested in logarithms. That is also one of the reasons I showed you a numerical table in Wright. Immediately the persons who got very interested by the work of Nepper was those which were accustomed in constructing numerical tables, which were used in computations. Here you saw in computations needed for performing this grid. Because they immediately understood that logarithms made such computations much more rapid. So, Halley, who was a great friend of Newton, and perhaps you know him from the comet Halley, in my youth, when I was your age, we all learned about comet Halley because it passed. It was visible from the Earth in the 80s. Now I think it will be visible from the Earth, I don't know, in 100 years. So I don't know if you heard about it, but in any case, Halley was a very important astronomer in Great Britain at the end of 17th century. And here is what he wrote in 1696. It was discovered by chance, and as far as I can learn, first published by Mr. Henry Bond, as an addition to Norwood's Epistome of Navigation, about 50 years since, that the meridian line was analogous to a scale of logarithmic tangents, this, of half the complements of the latitudes. So here is not the latitude is here, and a complement of latitudes. You have to know that if you see the word latitude, it means that you measure angles along a meridian. I chose to measure them from the equator, but another choice is from the North Pole. So if you want to understand precisely this sentence, it means that you have to go and make a drawing and to see from which point latitude is measured. This is something you have to do all the time if you look at ancient texts. You do not have to project on them your interpretation. The ancient text, in fact, is like a travel which obliges you to get out of your security zone, to see that there are variants of what you know which are perfectly viable in other contexts. So we discover that from what Edmund Halley wrote here, that probably this was discovered by Henry Bond, but there were other approaches in the 17th century by Harriot Gregory Hooke. And what I want to show you here is a geometrical approach of Harriot. Unhappily, he did not publish it. It was discovered much lately in his manuscripts, but it is wonderfully analyzed in a long paper of History of Maths of 1968 by Pepper, Harriot's calculation of the meridional parts as logarithmic tangents. It's another history which explains why Mercator's function, as I called it today, was called meridional part in those times. So, this comes from a second interpretation of Mercator's function, which I called mu of phi. So here, again, let's fix an angle here along the meridian, which is phi. And let's follow a rhumb line here, but at a precise angle of 45 degrees, or pi over 4. Our representation being conformal, it means that it has to be represented here simply as a line making 45 degrees here. So it means that in this representation, if we draw two meridians, and here's a parallel where the rhumb line intersects the meridian, this height, which gives you here mu of phi, is equal to this one, because here in the representation we have an isosceles rectangular triangle. This angle here is straight. So what interests us appears as the length of this arc. And because here we are on the equator, it means that this length is the same one as here. So what does it mean? That if you want to know the height at which to represent this arc, You take this parallel circle here, you go along the rhumb line at 45 degrees till it intersects it, and now you draw this second meridian, and you measure here the length along the equator. So pay attention, now it means that the function we are interested in is that which transforms this phi into this length here on the equator. This is the question. How to understand this? And it is this function which has this expression. So we want now to understand why this function is represented as a logarithm of a tangent. The clue of Harriot's approach was to pass through a second projection, which is called the stereographic projection, which was known in antiquity, but the name comes from the 17th century. And here I use for representing it a drawing by Rubens from 1613, the same period. Here you see an angel coming with a fire, which allows the celestial sphere born by Atlas to give here a shade on the soil. And now imagine that the angel comes with the fire nearer and nearer till the fire is at the point of the sphere. So it means, imagine that the shade is produced from a point of the sphere. Then this is called stereographic projection. In fact, not on any plane. If you are on a point here and say that this is your North Pole, or say the North Pole on this sphere is here, the stereographic projection from that point means to project the sphere centrally from there on the equatorial plane. This is stereographic projection. And a crucial property of stereographic projection is that itself is conformal. I won't prove this. This can be done elementarily. I'm sure some of you had already done that. Otherwise, it's a very good exercise. You work together to prove that stereographic projection preserves angles. It's a great exercise of space geometry. So we will use it. So here you see, in fact, a representation by Dürer. Stereographic projections were already known in antiquity, and they propagated in the artist world. And here you see a representation of part of the sky by Dürer under this projection. So I use the fact now that stereographic projection preserves angles. And what do you have to see here? I project from the North Pole. So imagine you are on a big round sphere which is in crystal, so you see it by transparency. And your eye is at the North Pole, and you are looking towards the South Pole. So here, this point is the South Pole. And now the meridians are seen by you as straight lines getting out of that point. So all of these are meridians. And all the circles centered here are the parallels. So here what we see is a region near the South Pole. And the instruction to have a rhumb line is an instruction at each moment to go in a direction of fixed angle. And here I said that I use the angle of 45 degrees. And I said that my projection is conformal, which means that my instruction is not changed. The problem transfers to a problem on the plane. At each point, I have to have a curve which goes in this direction. So this is a drawing I did here by drawing segments at 45 degrees with a radii everywhere. And I think that when you look at this, you have a dynamical impression. You see that something is happening. Normally, you see here lines, even if they are not drawn. Your mind obliges you to see lines which go towards the center. And here you don't know exactly what happens. And I think here you see a little the origin of the first belief of Nunes. Why he said they go to the center. Because even if you are very careful and if you draw a lot of such segments, well, here I follow it and it seems to go there. But in fact, it does not go there. But I am at the limits of my technical capacities with a pencil. The region gets so small that I cannot represent more segments. And we will understand that this is what happens because we will see that this is related with logarithms. And you know that logarithms are inverses of exponentials. And you know that exponentials are used in everyday expression to speak about exponential growth. But exponential growth is the same as, say, logarithmic decay. And logarithmic decay is exactly this graphical phenomenon, which means that there we cannot decide just by drawing by hand what is happening. And in fact, what is happening is an infinite spiraling. And what will convince us that it is spiraling won't be the view, because here we cannot view that. It will be the computation. And there you see precisely how formula pop up at moments when the vision does not give us the answer. So let me show you what meant to do differential calculus in the 17th century in a geometrical context. This way of doing is very poorly taught nowadays, but I found it absolutely magistral because it's related really to the way of thinking about maps at the time. So what are we interested in? We want to find lines, which I represent here, curved lines, which make a fixed angle with all radii here, and also with all centers, a circle centered at the point, which are called south because it's the south pole, seen by stereographic projection. Here is a preferred circle, which is the equator. When I look from the North Pole, I see the equator. And the part inside the circle is the south hemisphere. And the north hemisphere, which comes to my viewpoint, gets projected outside the circle. So here what I want to understand is what happens with my rhomb lines in the north hemisphere, so when they get nearer and nearer myself. So thinking in differential geometry means to think in terms of differentials of quantities, called dr. But differentials of quantities, as were performed by Leibniz and then by the Bernoullis and Euler and all of them, were to think that at the limit, some pieces, objects, when they became infinitely small, they became plane geometry. So in particular, this is a curve. But I look at a very small piece of this curve, here between one meridian and the next one, and I say that the difference in longitude is d lambda. Just by the act of writing d lambda, it means that I have to think this as very small. But pay attention, if I want to understand what happens, I don't have to draw that angle very small, otherwise I won't have the place to draw the rest. So here is the art of differential calculus, is that you have to draw big, such that you see something, but then you have to think small. And you think small due to this notation. The D tells you this is small. Here I say R. I don't have a D in front of the R, which means that this is not small. This is any radius. What will be small is this angle. And here, if I go at a circle of distance R from the origin, you see that the length of this arc is dilated by R, because d lambda, I measured it on a circle of radius 1. So here this length is R d lambda. And now I look this arc till it intercepts this second line, and I am looking at the second circle. So I get a new radius. This new radius, if d lambda was small, this will give me a small segment, which is a difference of the two radii, so which I call dr. So here I see a curvilinear triangle, in which here I have dr and here r d lambda. This triangle has an angle of 45 degrees here. And now I use that those are small. To do geometry, means that this triangle being very small, this arc is straight. All the arcs, when they are sufficiently small, are straight. So being straight, here I have an isosceles triangle. So for infinitely small triangles, what I say is that these two lengths are equal. So you see, the equality comes from the angle of 45 degrees and from the fact that here I have a right angle. So the equation, which is a differential equation, because it's an equation between differentials of quantities, is dr is equal to r d lambda. And here it's a perfect example of one of the easiest differential equations, which are called with separable variables. By an algebraic trick, you can separate the two variables r and lambda just by dividing by r. So you get d lambda is dr over r. And now you integrate this along the curve, and on a big part of the curve, integrating means that you make these infinite sums of Leibniz. And so here I integrate from 0 the lambdas and from 1 the radii, meaning that I decide, in fact, to start measuring from a point on the circle of radius 1 here, and there I decide that I start on the meridian 0. So I measure, in fact, the lambdas from 0. If I decide to measure like this, I get the integral of d lambda from 0 to lambda, but this is lambda, is equal to the integral from 1 to r of dr over r. And this is one of the definitions of the natural logarithm of r, as an integral of dr over r. And we get lambda is the logarithm of r. And let us see why this tells us that we have spiraling when we get nearer the pole. We said the nearer the North Pole means that here r tends to infinity, because this is outside part which is near the North Hemisphere. So when r tends to infinity, you know that logarithm tends to infinity. So lambda tends to infinity. But lambda is a measure of longitude. So tending to infinity means that you turn and you turn and you turn to infinity an infinite number of times. So this line will go to infinity in this precise way, but turning an infinite number of times. But infinity comes from my viewpoint on the sphere. So in fact, this is how I see a spiraling which gets nearer and nearer myself. So that's why we have spiraling. But because of this logarithmic law, you saw that if we try to be correct from the Euclidean viewpoint, we do not see this turning, because it turns getting so rapidly towards the point that our eye does not see that phenomenon. In fact, this, if we come back, let's see here, you see that the problem which leads to these curves, if you take this picture and you dilate it, you make a homotopy, the picture is transformed in itself, because a dilation does not change angles. Being sent in itself, it means that the system of curves, which we call the integral curve of this differential equation, is sent into itself. But all these curves are the same. If you take one, you see that by rotating it, you get curves which are solutions to the same problem. So this tells you that these curves, which are called logarithmic spirals, because in the expression you have the logarithm, by homotopy are transformed into themselves. You can take them at all the scales and nothing changes. It's not like a circle. A small one by homotopy becomes a big one. No, a logarithmic scale does not change. This fascinated Jacob Bernoulli, one of the first of the famous family of Swiss mathematicians who learned differential calculus from Leibniz and developed it a lot, and who also taught mathematics to Euler afterwards. And this fascinated so much Bernoulli that he asked a logarithmic spiral to be represented in his funeral monument in Basel. I told you about Norbert Acampo before. He lives near Basel, and he brought me there. And I saw this. Do you see the spiral? It's here. But it is not logarithmic. Here you see that it turns several times around the origin. With a true logarithmic spiral, you do not see it. I showed you that it was a problem of Nunes. His error came from the logarithmicity. Well, probably that Jacob did not leave precise receipt for the artisan who did that. The artisan represented an Archimedean spiral. The Archimedean spiral has a property that if you go on a ray here, you get equal segments. So this is very easy to draw and to see. No, the logarithmic one does not make equal segments. You have an exponential change of the length of the segment. And this is not the spiral which Bernoulli admired, but you see, this tells you that when you communicate mathematics with somebody who is not a mathematician, you have to be very careful. And it's a lesson for your lives. I think even if you don't become mathematicians, your lives will deal with science. This, for me, is a sign that you have to be very, very careful when you communicate science. It's difficult to communicate it precisely. So I promised you to show why we arrive at this formula. So let's see. The idea was that we pass through the stereographic projection. So first of all, we will project from the North Pole on the plane of the equator here. So then our drum lines, say I take one here, going in the North Hemisphere, and we said that this gives, after stereographic projection, a line getting outside the unit circle, which is here. And we know, we just saw that here the rule is lambda is a logarithm of r. Here, what we learned on the sphere is that this lambda here is in fact the Mercator function of phi. This is the interpretation we saw first, that we can see the Mercator function directly on the sphere here. So we have these two relations. This tells us that mu of phi is logarithm of r. So you see that this gives us already the fact that mu of phi can be interpreted as a logarithm of something. Of what? Of this radius. But now this radius, we will think about it in a different plane. Here we thought in the plane of the equator. Now we will think of it in the plane of the meridian. So projection from the North Pole. So you see it is this segment, OP prime. And let me extract it here. So you see in this segment you have R here. And you see that we have a right-angled triangle with height, which is the radius of the sphere, so it is 1. So here we have 1. And now if we look at this angle, because this is phi, an easy computation tells you that the angle here is pi over 4 plus phi over 2. So this angle is this one, of projection from the North Pole. So, because this is 1, we have this angle, r will be the tangent of this angle. And now putting everything together, you see that mu of phi is lambda, which is logarithm of r, that is the logarithm of tangent of pi over 4 plus phi over 2. And I promised you that every piece of the formula will get interpreted geometrically in the figure. And you see that, moreover, we understand that to understand this we need a special projection, stereographic projection. We used in a strong way the fact that it is conformal in order to make the logarithms pop up. And then the geometry is to be thought both equatorially and meridionally. So you understand why these planes are particularly important to study the geometry of a sphere. So I don't know you, so perhaps this is due to the fact that what I prefer in mathematics is geometry. But I am very happy. Each time I repeat this proof, it makes me happy. Now I am happy. If I could not pass this happiness to you, it's my fault, but it may be also the sign that you prefer another part of mathematics. And this is very good that we do not like all the same thing, because we need many tastes in order to deal with the problems of the world. I will finish now by showing very rapidly some connections with something else. What connection could we have with a clock, like the clock of Cédric Villani? He has a clock here with a chain. Yes. And Claude Perrault, exactly this kind of clocks which existed in the 17th century, Claude Perrault was the architect of the part of the Louvre built at the end of the 17th century, what is called la colonnade du Louvre. If you look towards it, for those of you who went to Paris, you look at the eastern part of the Louvre, and you look at it and you have a lot of columns. That is due to this architect, Claude Perrault. And he was a brother of the Perrault of the stories for children, if you ever read the stories of Perrault. And he asked a question to Leibniz around 1670. He took out his clock, and this is a modern representation. So this did not exist at that time. This is a picture I took from a book called Mathematics and the Imagination by Kastner and Newman. By the way, it has nothing to do with Mercator. It is in this book that was introduced the word gogol for a very big number. And in the footnote, the author says that they asked to their nephew, who was, I don't remember, 5 years old or 8 years old, for a new word for a very big number, and for some reason, he said gogol. And this was the origin of Google, when they searched for a name for something which could deal with huge amounts of pages and of information on internet. They deformed that word which was introduced in this book. So this is a book telling you a lot of short stories in all kinds of mathematics, and with nice illustrations like this one. So here you imagine that you have this, how do you call locomotive? Engine, let's call it engine, and you have your clock which is attached to the engine, and the engine goes straight, and then the clock follows. But the clock will follow along some curve, and this curve is called a tractrix because it was tractioned by the engine. And you see that it gets nearer and nearer the rails. So in fact, this is a curve which starts here, in fact, vertically. The tangent at the starting point is vertical because initially the clock was vertical, and then it has an asymptote here which is horizontal. In fact, this curve is intimately related with Mercator's projection. In the following way, I told you, imagine that here you have again a meridional cut of the sphere, and we want to know this point P of latitude phi, where to represent it here at height mu of P. So to get a geometrical construction, you can do this. You put here in red the tractrix, which starts from this position of the clock, here, horizontal. And then with asymptote, which is this tangent to the circle. And now if you have OP here, you move this segment parallelly to itself till it is tangent to the curve. And then here the second vertex will give you the height mu of P. So in fact, you see you have to move tangents here, the tangents to the tractrix. The parts between them and the asymptote have equal lengths. It's a property of the tractrix. The length is equal to the length of the cord of your clock. And this construction is exactly that which allows you to do the Mercator map. A second thing is that this expression, tangent of pi over 4 plus phi over 2, has a second expression, as secant of phi plus tangent of phi. the second of an angle is simply 1 over the cosine of the angle. So we come back to our friend 1 over cosine. Here, it's a proof. The proof is here, is this drawing. I love such proofs, because you are here and you have to see why this drawing proves that formula. It comes from a paper by Roger Nelson, Proof Without Words, a trigonometric identity for the secant of x plus tangent of x. In fact, Nelson published some books with such proofs. They are very nice. You have one proof per page with a drawing. I think you would love that. So I leave you 30 seconds. Try to understand the proof. So the starting part of the figure is this green triangle here. You elect x. X is a phi of before, but this is a notation from the paper. So here you see the part of the circle of radius 1. So that's why here this segment is of length 1. And then you take the tangent to the circle there, and you get a triangle. And because the tangent is perpendicular to the radius, here the angle is of 90 degrees. And because this is 1, this you will have the tangent of x. And also this will be the secant. And this is also the drawing which explains the name. You see that this segment is tangent to the circle, and you see that this one is not tangent, it's secant to the secant. That's the reason of the name of the secant of x. And then you do something else. Next part of the figure is to complete it here by a straight angle. You arrive here on the circle and you join with this point and you continue till you arrive here. So because this is a radius, this is 1. And now if we look at the angle, this is x, so this is pi over 2 minus x. And here we have an isosceles triangle because we have 2 radii of the circle. And this allows to see that this angle is pi over 4 plus x over 2. That's why you have this pi over 4 plus x over 2. And in this big triangle, because this edge is 1, this shows that the opposite edge, its length is tangent of pi over 4 plus x over 2. So the right member of the equation is simply the length of this side of the big triangle. But now you see geometrically the big triangle divided into 2 segments. One of them is, as I told you, of length secant of x. The second segment is this one. And now let us look here. You see that this angle is a complement of this angle here. But we said that this angle is equal to this one. But also this angle is a complement of this one because in the middle you have a right angle. So it means that these 2 angles here are equal. So this right blue triangle is isosceles at this vertex. This means that this segment is equal to this segment. But this segment, we said that it was tangent of x. So that's why this is equal to secant of x plus tangent of x. So you see that you get much more than the equality. You get geometrical interpretations of all the parts of the equalities. You see everything there. So that's why I like these things. I don't know people who find these proofs, how they find them. For me, it's a mystery. But from the community pop out from time to time, like beautiful flowers, such proofs. So if you find such proofs, please tell me, because I love them. And why did I tell you this? Because the second writing makes appear that you see secant of x plus tangent of x. Think analytically. 1 over cosine, it's an even function. Sec of minus x is equal to secant of x. And tangent of x is an odd function. Tangent of minus x is tangent of x, minus tangent of x. And now take the Taylor expansion of this. And the Taylor expansion, you write it in this way, by its coefficients multiplied by the powers of x, x to the n over factorial of n. And it turns out that the coefficients we have here are all integers. And in fact, these integers have a combinatorial interpretation. For instance, what is this 16? It's a kind of musical interpretation. You begin to sing, and then you say, well, now I lower my voice. And you will sing with only 5 notes. 5 because I am looking at x to the power 5. So I put at 5 horizontal lines, and then I want to get down and up and down and up and down and up. Every time it's like this. How many melodies qualitatively we have of this kind? It depends on the relative positions of the heights. You see here, for instance, what's the difference between this and this? Is that these 2 points are interchanged. This one is lower than this one, but here it is upper. And you try to draw all those melodies. And you can see that with 5 lines, you get 16. Well, that 16 is the coefficient appearing here. So if you put 6 lines, it turns out that you will have 61. So you see that inside this function, which controls the Mercator projection, we have the shapes, in fact, of all the melodies, this kind. In fact, this can be also interpreted from the viewpoint of modern mathematics as shapes of Morse functions in one variable, or of landscapes with one variable. In any case, why? You see, this is a relation with combinatorics. I have absolutely no idea. For me, this is a curiosity, but I wonder if there is a more global viewpoint in which some relation like this between cartography and combinatorics appears. I have absolutely no idea, but I find this extremely amusing. So if you want to learn more about the Mercator projection, I put some pages here with references. Also, this is very interesting because a paper by Gaspar and Leitao here explains the error of position of Africa in that map by the fact that at that time the magnetic properties of the Earth were not well understood. If you go now following your compass in a fixed direction, at each moment you use your compass, but your compass does not show the geographic north or east. It shows the magnetic ones. And the magnetic one does not follow an easy grid of meridians and parallels. And the way these magnetic declinations varied on the Earth began to be understood only in the 18th century. That's why, in fact, Mercator charts were not used in navigation before the 18th century, because of problems, magnetic ones. And here they show that now with what we know about the magnetic field in that time, that the position of Africa comes from the data Mercator used about the magnet in those times. Well, I made you understand that there is spiraling, but it would be good to see this spiraling. So I found no better way than showing you a drawing by Escher from 1958. So here you see some of these loxodromes on the Earth. But you see only one spiral, and I told you that there are 2. It spirals both to a pole and to the other one. Well, happily, Escher also made a second representation in which you can contemplate the 2 spiraling phenomena. Well, I hope that I could interest you in those rumblings and all the spiraling phenomena, and that now you understand why I was speaking about spiraling straight ahead, because all the problem was to transform a spiral in a straight line, and I thank you very much for your attention.
Thank you, Patrick, for another beautiful talk. We have time for one question before we get kicked out of the hall. No? Sure? Tired? Okay, let's continue tomorrow afternoon at the French Institute. You'll have more opportunities there to ask questions to our lecturers. Thank you, Patrick.